So in this case, the alkene is over here, and we're adding a hydrogen and a bromine across the alkene. The bromine would go on the more substituted carbon. So hydrogen would go over here, the new hydrogen. And bromine would go on the secondary carbon. So let's rewrite what we just did. If you were to do the same reaction, but in the solution you also include some peroxides, what would occur in this case? In this case, the bromine would go on the less substituted carbon. It would go on this carbon. Go ahead and try this problem, and let's include peroxides again. So again here, bromine will go on the least substituted carbon. So across the double bond we have a carbon here that's secondary because it's attached to two other carbons. And then there's one that's, well, this one's not really secondary, is it? It's tertiary. 3 carbons. And this one is primary because it's attached to one other carbon. This one. So the bromine would have to go here. So that's where it goes, not here. If you were to do this reaction with HBr without the peroxides, it would do this. Go ahead and try this problem. What would happen if we add HBr? In this case, we're going to get a product that looks like this. This looks pretty counterintuitive. You might think, why is the bromine going all the way over here? And to understand this, we have to look at the mechanism for the reaction. So let's go over what the mechanism would look like in a more straightforward problem. So let's say here, right, if you do this reaction on the bottom, you will get bromine on this carbon. However, there are steps here. So the first step is that the pi bond electrons would act as the nucleophile and try to attack this hydrogen and take it away. So then the electrons that are between the bond of the HBr would just go away, do the bromine, and the hydrogen would go on the less substituted carbon, would go on this carbon. So there's an extra hydrogen here. And the other carbon, this one, would bear a positive charge. Now the reason why the hydrogen doesn't go here is because then if it were to go here, you would have a situation like this, and the carbocation would be primary, but primary carbocations are not as stable as secondaries. So then at this point, we still have the bromine, which is now a bromide ion, and since it has a negative charge, it's pretty nucleophilic. It can go ahead and attack this positively charged carbon atom, and we get this product as the outcome. If we do this reaction on top, the mechanism starts the same way. These pi electrons are going to attack the hydrogen, and then the electrons from the bond are going to leave, and the bromine is just going to leave. So now we get a carbocation here with the extra hydrogen on this carbon. But notice now that we can do what's called a carbocation rearrangement. We can take this methyl group, not a methyl group, but we can take a hydrogen that's here, move it to this carbon, and now we have a more stable intermediary. We have a tertiary carbocation as opposed to a secondary. And the hydrogen, this hydrogen, we could have done it red or something else, right? Is now moved to over here. So that's called a hydride shift. Right? The hydrogen and the two electrons with it are going to shift to give us a more stable carbocation intermediary. And then the bromide ion that was there is going to attack the carbon that's positively charged, and then we will get this product. Now let's go over the mechanism for the peroxide reaction, where we have HBr with peroxides added. So first try and predict the outcome of this without looking at the mechanism or doing the mechanism. It would be bromine added to the last carbon. But how does this actually occur? So the mechanism for this is that the peroxides are going to induce radical reactions. So whenever you have a peroxide, you have an oxygen-oxygen bond. And this is a pretty weak bond, so it's very easily going to break. But it's not going to break the normal way. It's going to break like this. One electron from the bond is going to go to one oxygen, and the other one is going to go to another oxygen. So we are going to get an R group, which is any group of carbons or hydrogens, and an oxygen with a radical on it. So that's a single unpaired electron. Now past this point, you're going to react this with HBr, because there's HBr in the solution. And this is going to basically come together with one of the electrons, and one electron is going to go to the bromine. So we're going to get ROH on one side plus a radical bromide. or radical bromine atom. This radical bromine atom is going to come in and react with the alkene. Now, one of the electrons in the alkene pi bond are going to form a bond with the bromine. One of them will go to a carbon. Now, the question would be, what is the outcome, right? The outcome could be that we form a radical on the primary carbon, then on the tertiary carbon we have the bromine attached. Or we could have another situation where we form the bond with the bromine on the primary carbon, then the more substituted position takes the radical. Which situation do you think would be more stable? The situation that would be most stable is this bottom one, because similar to carbocations, the radicals like to have more be on more substituted carbon. So this primary is not very stable, but this tertiary radical is more stable. So this would not occur, or at least not as often as this. At this point, this can react with any HBr molecule in the solution. This would contribute one electron. One electron from this bond would be here, and the bromine would gain one electron. So then this goes to here. We get that outcome. And that extra hydrogen atom, you don't have to draw them because we usually don't in these structures, obviously. But if this hydrogen atom is in purple, it would be going over here. Now, as a result of this reaction, we also get the bromide, or the bromine radical, because this would gain an electron. And this would go back over here and just do the reaction over and over and over again until all the alkenes in the solution have reacted. And at the end, there has to be a termination of this. So this bromide radical can react with anything, let's say another bromide radical. This would contribute an electron and this would contribute an electron, and they would form bromine. Or it can react with any other thing. So it can react with this potentially, although I don't think this would be a very stable bond. These can form a bond like that. However, it's going to end. But at the end, you should get a product, or at least at the end, you should have no radicals. You should always show that at the end when doing these. Alright, so I think that's good with the hydrohalogenation.